Okay, so welcome back. So, in the last lecture we understood the regret guarantees. Okay, so now if you remember the next thing, so which is so we understood the regret guarantees, and in the first lecture we basically tell there are regret guarantees and there is something called the PAC guarantees. So what is PAC means? PAC is, the full form of PAC is probabilistically approximate correct. Okay. So I have PAC which is probabilistically approximate correctness guarantees. Okay. So, what does it mean? As we discussed in the last lecture, it means that now I am not looking at the regret, but what I am looking at is how fast I converge to the best arm, right. Now, the problem is you cannot basically say which is the best arm, because it depends on how much the reward difference is. At least in the last lecture we understood that the higher the reward difference, the lower number of samples you will be required to identify the between the two arms, but if the reward difference is very low, then you will take much higher samples, right. So, we do not exactly ask for exactly the optimal arm, but what we want is basically at the end of some number of rounds, let us say t prime, after t prime what I want is, I want the algorithm to output an arm, let us say I, such that the difference between mu star minus mu I is basically less than or equals to epsilon, and because this is the stochastic setting, I can't say this with highest with deterministically. So, I say that the probability that mu star minus mu I less than equals to epsilon, this should happen with high probability 1 minus delta. Is the question, is it clear? So, what I am saying is that whatever after time t prime, whatever output the algorithm is giving, this arm I should be epsilon close to the optimal arm with high probability. That's what PAC guarantees means. Is it okay? Perfect. So, now if you understood the last lecture, then you should be able to know that this t prime, when I am saying that this is the best arm I which satisfy this property, this t prime will depend on the parameters epsilon and delta. Okay. So, higher the values of epsilon, higher the values of this delta, lower will be the t prime. If I am giving lower guarantees, then I will converge to the lower guaranteed arm faster. Okay. If I want better guarantees, then it will take more time for me to converge. Okay. So, this is another kind of problem statement that we basically see. So, given parameters epsilon and delta, find an epsilon optimal arm with probability of at least 1 minus delta. And what is epsilon optimal arm? Epsilon optimal arm is the arm which is epsilon close to the optimal arm. Okay. Now, what you can prove, again here I am just going to give you just some things and you can just do, again it is the simple applications of Hofding's inequality. What you can do is that you can basically prove that it is sufficient to pull a suboptimal arm total of order 1 by epsilon square log 1 by delta times. Okay. Why I am saying it is a simple application of Hofding's? If you substitute this 1 by epsilon square log 1 by delta into your Ni term in the Hofding's inequality, you will exactly get that. Just try it out. Okay. So, then again you can basically say that it is enough to pull these many times. Okay. This is easy. What you do, if you want to satisfy pack guarantees for a given epsilon and given delta, you basically pull these many number of times, okay, and this will be your algorithm, okay. But again the similar thing you can ask, okay, why we are not restricting our search space. We did this here, right. So, here also what I am doing is, I am unnecessarily exploring the arms which are too far from the optimal, okay. One arm may take this much time, the other arm may take lesser number of times to basically recognize whether it is not the optimal, it is not even close to the optimal. So, I need something, okay. Then we have some algorithm which is called the successive elimination algorithm, okay. And the idea is simple, as like idea is very similar to what we saw in the earlier class, okay. Here what you are doing, as the name suggests, I am not interested in the total reward, I am just interested in finding the best arm, okay. So, initially you basically assume that everything is best, okay, and then what you do, you keep exploring within this best framework, and then somehow you realize that one arm is significantly worse than the other, and then you eliminate it, you basically shrink your search space. Now, the badness, intuitively the badness is defined by these lower terms, okay. So, now imagine at a particular point, this particular person, the UCB is here, okay, and the LCB is here. So, UCB is here, LCB is here, and for this arm UCB is here and LCB is somewhere, okay. So, if this arms, even the UCB is less than its LCB, then this arm is definitely bad with high probability. Understood? So, the arm you are eliminating, if its UCB is worse than, if its optimistic reward is worse than the pessimistic reward of some arm, that means this arm is not going to work out. You can eliminate this arm, okay, and this is the idea behind the successive elimination thing, okay. That is what it is. The entire math is basically, you basically try and keep removing the arm, okay. So, I am not going into the detail, and this is the algorithm.
Those graphs were like rewards are always 1, those graphs are showing the probability that that arm will give us the reward 1, right. The blue lines are the true values.
Blue lines are the true values, and what we did, we basically, so this orange bar is the optimistic reward, this particular person is the pessimistic reward. You
reward meaning this blue bar, so in our case where we took 1, 2, 3, 0.1, 0.7, 0.8, so these are the, so blue lines are those, right.
Okay, so let me tell you again. So, I had 1, 2, 3 arms, blue lines are mu1, mu2, mu3.
These are the probabilities.
These are the true reward, true probabilities. This I do not know. I mean, for the figure I have basically written it, but I do not know this, okay. This is not known. What I am doing, here I have mu1, here I have mu2, here I have mu3. I just plotted on these 3 which I do not know, okay. This particular term basically denote mu hat 1 n1 plus square root 2 ln t divided by n1. This is the upper confidence bound, okay. And this person here, this bar here denote mu hat 1 comma n1 minus square root of 2 ln t by n1, okay. From the Hofting's inequality, I know that, I do not know mu1, but I know that with high probability mu1 will lie between these 2 bars, okay. And this is what I am doing for everybody, okay. I pull this arm, okay. If this person decreases, significantly, and so this person will always increase. No, so N1 will decrease and this person will, so this person will also decrease because N1 is increasing linearly, T is increasing logarithmically. So if I am pulling this arm, this person will decrease, okay, until and unless this person increases, this person will decrease, okay. So if the I get the reward of 0, this will definitely decrease, okay, and this will definitely increase, okay, and you just keep on pulling the arms in a round robin fashion, because here you don't care about the reward that you are getting, okay. Now at some point, because this person is really bad, at some point this UCB will come here, okay, and this LCB will go here, okay. Now because you know from the Hofstad's bound that with high probability the true mean lie between these two things, okay, this person is not good with high probability. With high probability you know delta, matlab there is a possibility that it is good, but my interest is in delta, okay. So then you can just remove this person, okay, and then you keep on removing it until you are basically you get one person which is good enough for you. And these, in this pack learnability, the UCB and LCB you define based on these epsilon and delta. That is the intuition, okay. Good. So I guess that is all I had in this. So let me now come back to the connection with game theory. So now what I want to do is I want to tell you something that I have worked on. We understood the multi-arm bandits, we understood the applications, we understood the algorithms for it, okay. Now we will basically connect it with the mechanism designer auction theory that you have already read, okay. So and then I will see, I doubt it, but if the time permits I will just tell you some application to demand response, okay. Okay, so here the idea is of this talk is basically to tell you the existing results in this literature, okay. So I won't go into too much technical details to it, I will just give you the pointers if you want to read on, but the basic primary idea is to just let you know that these things exist so that you can basically go and read the relevant area if you want, okay. So multi-arm bandit problem we have already discussed, stochastic bandits we are here, we understood the stochastic bandits, we want to minimize the regret, we understand this, okay. Mechanism design, are we okay with it? Sure? Pakka? Okay. Then I will just skip it, okay. Let us go back to the motivation, okay. So now what I am trying to do in this part of the talk is that I am trying to connect the multi-arm bandits with the auction theory, okay. The first question that you should ask, why, okay. So then I go back to my sponsored search auction, okay. So now what happened is in the sponsored search auction is the same thing. I have the sponsored search, sponsored ad slots, but and the Google wants to auction it, but Google doesn't get the money from Nikon or Canon or Samsung until and unless somebody clicks on it, okay. So if Google had to decide which ads should get these slots, then how should it decide? It should explore first, but let us say these click probabilities were known, let us assume. So if the click probabilities are known, so then what it does, it basically asks each and every advertiser to basically tell how much every ad is willing to pay Google for a click, okay. So that is the valuation. So, what is a valuation? It is a valuation of a click that each advertiser is willing to pay for a click. Okay. So, now with a particular advertiser, with any advertiser I have two things associated with advertiser I. Okay. What are the two things? One is the mu I, which basically represent the click probability. That means, if this advertisement is shown, then with what probability this advertiser will be clicked. Okay. And the second thing is what? Is the valuation per click. Okay, we understand this. Now, which ad? So, if you would know this mu I and vi, then which ad should Google put? It should whichever is the maximum mu I into vi. This is the expected reward. Okay. So, now what I am doing? I am trying to find the ad which has the maximum value of mu I and mu I into vi. Does it make sense? Perfect. Okay. So, the question is, mu I is not known, I need to learn it with the bandit feedback, and vi is strategic. You want a truthful elicitation of these vi's. Okay. And this particular area is called the multi-arm bandit mechanisms. You are trying to design the mechanisms under the framework of multi-arm bandits. Make sense? Perfect. Other applications are smart grid, crowdsourcing, reverse auction, the similar thing. Here, every time you are posting a task, the workers are doing the task with some quality, and then you are basically paying the workers. So, every worker will bid for the cost that it takes to spend that much time, and then you are basically paying it. Reverse auction and smart grids, I will see if at least I can tell you the problem formulation. So, let us skip it for now. Okay. So, the question is the following. We all understand now at least reasonably well how to learn these mu i's. We know this, right. So, what will you do? You will basically apply the multi-arm bandit algorithm to it with a simple modification, that earlier we were saying that the reward of the arms are simply mu I. Now, the rewards of the arms are not mu I, but they are mu I into vi. Right. So, you will basically try to pull the arm with the highest mu I hat plus vi, because you do not know, because you want to apply the UCB here, then what will you do here? Is the question clear? No. No. So, my question is, I want to choose an arm, let us say vi is not strategic, you know vi, okay. You are learning mu I, okay. You know how to learn mu I, we have already done it. Which algorithm would you apply? Let us say upper confidence bound algorithm, okay. But now you are not selecting the arm with the highest mu I, but you are selecting the arm with the highest mu I into vi, okay. Then what will be your algorithm for that? You will basically find the optimistic value of this. What will be the optimistic value of for this? So, you do not know this, okay. So, if I simply try to pull the arm with highest empirical reward into vi, then I know I will be in problem, because then I am not exploring, hai na? That was the precise problem, right. So, then what did I do? Instead of mu I hat, what I did? I basically pulled the arm with certain optimism, okay. So, instead of this, what I will do? I will basically pull with respect to this, okay. So, for each ad, I will maintain mu I hat plus square root of 2 ln t by ni, multiply it by vi. whichever will have this, I will pull this. Simple. Sorry. Is it clear? Okay, perfect. The problem is what? I want the mechanism design. Okay. So, let us talk some definition about the mechanism design. I think you have already seen this. Okay. So, what is normalized mechanism? Normalized mechanism basically says is that if the agent bids 0 valuation, this agent should get the 0 payment. Okay, simple. The truthful mechanism is, we know incentive compatibility, right? Each and every agent should bid its truthful valuation, right? So, these are some of the information. Now, as I said, I will just capture the results and will tell you the intuitions why those results happen. Okay. My first result is, like we have in the mechanism design, lot of impossibility result. Here also I have the first impossibility result. The first impossibility result that came in 2009 basically said that if there is any MAB mechanism which is normalized and truthful, then it has to be exploration separated. Okay. So, let me tell you what does it mean. So, let us first understand the exploration separated. Okay. What is exploration separated means? As the name suggests, a mechanism or any algorithm is called exploration separated when the exploration rounds are completely different from the exploitation rounds. Okay. So, in these cases, none of your the algorithms which are UCB based, bound, shrinking the search space or epsilon greedy, or these algorithms will not work. So, exploration separated algorithms are the algorithms where what you are doing is, for a fixed number of T rounds, you are basically exploring which arm is better, and after that T rounds you are choosing which is the best. Exploration is separated from the exploitation. Okay. What this result says is that when you have a problem like this, where you want to basically find or learn these mui's, at the same time you want to elicit this valuation truthfully in a reasonable world where you also want your mechanism to be normalized, then this can only happen when your mechanism is exploration separated, when your multi-arm bandit is exploration separated. Okay. And the intuition is as follows. Okay. But before this intuition, this exploration separated is really bad, because what we saw earlier is that the regret, if I see the regret in the UCB based algorithm was how much? It was of order of log t. Remember this? Okay. Whereas, in exploration separated, what happens is the best regret that you can get is t to the power 2/3. Before that, how will you prove the regret of exploration separated? What will be the idea? Let us just think some time. Okay, so exploration separated is the following. So, the exploration separated algorithm will look like this. Can I write here? I think. Okay, so the exploration separated algorithm will look like this. You will have something called exploration phase, where what will you do? Let us say for T prime rounds. Okay, so for T prime rounds, what will you do? You will simply select arms in round robin fashion.
Could you write a bit bigger?
Okay. Okay, so for T prime rounds, you will explore, that means select arms in round robin fashion. Okay, this is what you will do till T prime rounds. You will simply explore. Okay, so each arm will get how many? So what will be the ni of ni T prime after T prime rounds? What will be the number of times arm I would have been pulled? It would have been T prime by k round robin mein. Okay, so you get these many samples for each and every arm. Okay, after T prime rounds, what will you do? You will exploit. Okay, so after T prime rounds, you will compute mu I T prime for all arm I, which is the empirical reward. And what will you do? Yes, after that, pull arm with maximum mu hat I T prime. Okay, so your arm pulling will be find the maximum. This is the exploration separated. That means you don't have the option to shrink the space. Make sense? My question is, how will you find the regret of this? How will you at least attempt to prove the regret? Let's just do some brainstorming over this.
The optimal arm minus.
Yeah. How will you do? How will you attempt?
The regret then shrinks to the first T prime attempts.
Yes. So there are going to be two components for regret. One is for the entire T prime rounds, you are going to make some mistake. You are going to basically incur the regret. Let's say the maximum regret, which is 1. So for T prime rounds, regret is for sure. For the remaining capital T minus T prime rounds, the regret will depend on how close you are to the highest arm. Now there is a dilemma. If you have T prime higher, if the T prime is large, that means thus you will make lesser mistake in your exploitation. Okay, but more on exploration. Okay, if your T prime is lower, then you are not making much mistakes here, but you may be too far away from the optimal. So you basically write your regret term with respect to T prime. T prime I will incur this much, and then if I have only mu ni T prime rounds may explore, then what is the probability or how much different I will be from the optimal arm. Okay, and then you have a regret term, you basically minimize it over T prime. Okay, and that would give you T prime to be somewhere of the order of T to the power 2/3. Okay, and that immediately gave you the regret T to the power 2/3, because T to the power 2/3 time you are exploring. Okay, therefore you get a regret of T to the power 2/3. So balancing exploration and exploitation will give you T to the power 2/3. Just focus on the intuitions here. Is it clear? Perfect. Now the problem is, we made a huge jump from ln t to T to the power 2/3. It's quite high. Okay, so what went wrong in the map mechanism? Why this exploration separated part? Okay, what went wrong is the truthfulness is the following. If you have seen, if you understand the auction theory well, the problem is when we talk about the truthfulness, most of the time we are talking about the truthfulness in the strongest sense. What do I mean by strongest sense? Dominant, strategic, incentive, compatibility. Have you heard about this term? What does it mean?
Without being truthful, it doesn't improve the utility of any.
But why dominant? Dominant is the primary thing here.
Irrespective of the strategies of other.
Exactly, irrespective of the strategies of the other players. No matter what other players are doing, I should be truthful. This is what DSIC mean. Okay, whatever the other person is doing. Okay, if I carry forward this definition to the MAB mechanism, okay, now in MAB mechanism another uncertainty comes, which is coming from the clicks. Okay, so now you are saying, you are not only saying no matter what other person is doing, you are also saying no matter what happens to the environment around me. Okay, so when I am talking about truthfulness here, I am saying no matter how the clicks are received. It could be really worst for me, and then I want to be truthful. Make sense? Okay, so you are not talking about stochasticity, you are not talking about anything, you are just saying no matter what clicks I am getting, I should, and no matter what bits other players are giving, I should be truthful. And this makes the problem really hard.
What do you mean by truthful here? Like, I am truthful about?
Valuation, right? So, VIs. Intuitively, why? Because I have this valuation VI. Okay, so because it is dependent on the clicks, okay, you can, so suppose if my probability is something, okay, let us say 0.5, and if I want to be truthful against all possible clicks, then it may happen that initially when I am getting too many zeros, and let us say if I value it $100, if I am getting too many zeros and if I value it on a higher side, then I may not get the slot. Whereas stochastically if I would have got ones and zeros, then I would have got the slot. So, you understood, right? For the same valuation, sometimes it is better for me to say $50, sometimes it is better for me to say $100. And because you are adversarial against all the possible clicks, this becomes challenging. Okay, the proof is rather long, so I am skipping it, but intuition is clear. Because you are talking about the highest possible truthfulness. Okay, so
I had a question
yes.
regarding what does normalized here mean?
So normalized here is, we saw, right? So normalized here means truthfully bidding, agent with zero valuation gets the zero payment. So you are not transferring any money to the non-zero thing. Okay, so just understand. So the main issue that we faced here was basically the fact that everybody, you know, you wanted the truthfulness against all possible manipulation, against whatever bits the other agents are giving and against whatever clicks people are receiving. Okay, but because we are under the stochastic multi-arm bandit setup, that's not required, right? So what happened if we fail to get DSIC?
We might have exploration increases.
No, so in general in the auction theory there are some impossibility result with DSIC. Have you done that? So then what did you do? What did you, in order to get rid of those impossibility results, what did you do? For example, GS theorem, right? So in order to avoid this, what did you do? Domain restriction. You did either the domain restriction, or if you go to the Dagwa mechanism, you basically restricted, instead of DSIC, you asked for the BIC, Bayesian incentive compatibility. So you restrict the things. You did not do, okay, but the idea is basically you relax those things, okay. So you don't ask the truthfulness in the strictest sense, but you kind of relax the things. Here also, if we intuitively think that do I really need this kind of truthfulness, the answer is no. I am not getting the clicks randomly, it is not an adversarial setting, okay. I am getting the clicks stochastically, okay. So then the kind of work that we did over a period of years is the following. What we tried to the kind of questions that we try to ask is the following. What happens? So here the problem was like everybody was basically you were basically targeting what kind of all possible click probabilities. So here you basically restrict the environment. You say that I do not know what is the click probabilities, even others do not know what is the click probabilities, okay. They do not know, they are also learning. So you assume that the kind of information that I have or the kind of information that the other people around me have is basically coming from the same learning mechanism. Whatever the algorithm is learning, that is the same thing that others are also learning, okay. The second thing that you can do is you can basically do some kind of weaker notations, okay. So you do not ask for the highest possible truthfulness, you basically say that, so what does this mean? This means that this is the utility that agent I will get with VI valuation, others are valuing something. So this is the history HT minus what is the utility when instead of VI it basically report VI hat, okay. In a truthful sense, what you want this term to be greater than equals to 0 for all t, no matter what the history is. In a strongest sense, what you want this term to be greater than equals to 0 for all possible t, right. So now instead of that you say that it is asymptotically truthful. It means that over a period of time, if I take the average utility by truthful bidding is better than the average utility by bidding non-truthfully. As the time increases, it becomes better and better for me to bid truthfully, okay. Understood the difference between the earlier notion and this notion. So earlier what I was asking this term minus this term to be greater than equals to 0 for all HT and for all t, okay. Now I am asking, I want this entire average to be greater than equals to 0. On an average I should be better, okay. The third thing is, interestingly, this impossibility result is only valid for a deterministic mechanism, okay. So this work basically in 2010, this was a foundational work in multi-arm bandit mechanism. They basically came up with a randomized mechanism which did something, okay. So it basically changed the allocation and did some randomization and showed that in that case you can work with your UCB kind of the algorithms, which gives good result. So let us not focus this, but let us focus on these two, okay. Questions? Okay, let's go forward. Okay, so what we proved, again please take references so that you can read if you are interested in more details. Okay, so what we did in this 2016 paper that appeared in AMAS, we proved that if everybody is learning over a period of time, that means when the click probabilities are not known to the advertisers as well as the mechanism designer, then you can actually design the efficient mechanism which are ex post individual rational and ex post incentive compatible. Okay, so let us understand three terms here. What is efficient mechanism? So, when we say efficient mechanism, it is efficient with respect to the regret. Okay, and what is the best possible regret guarantees that you can get? It is order log t. Okay. So, what we did in this work is we basically bought from t to the power 2/3 to log t, okay, while achieving what? Ex post individual rationality. What is ex post individual rationality? What is individual rationality?
Players will participate only if their utility is not negative.
Sorry?
Agents will participate only if their utility is non-negative.
Exactly. Agents will participate only if their utility is non-negative. There are two kinds of individual rationality, ex ante, ex post. Have you heard about them? No. Okay. No, Paka? Have you heard about ex post and ex ante? No. Okay. So there are three, sorry, ex ante, interim and ex post. Somebody are nodding. Okay, so let me ask them. Heard about it?
Ex post is after the game has ended or when the information is available.
Yes. Interim is during the game and ex ante is before. So which one is the strongest notion of individual rationality?
Exposed.
Exposed how many? Socho. Exposed how many? 1, 2. Ex ante how many? 1, 2. Okay, what about others? No, interim is not possible, right? It has to be the other extremes. So it's exposed. Why? Don't go to maths, just think intuitively. Okay? If somebody is individual rational, even if everything is known, that is what exposed is. Even if I know my valuation, even if I know the other's valuation, then also I am individual rational. What is ex ante? Ex ante is I don't know my valuation, I don't know other valuation, I take the expectation and then I am individual rational. Now you understood which one will be the strongest? It will be exposed. Because we are in this setup, what is interim? When I don't know others' valuation, but I know my valuation, then I take expectation of others. That is interim. Okay. So, when I am individual rational, when participation is best for me no matter what the valuation of others are, what the valuation for me is, then it must be the strongest sense of individual rationality, strongest notion of individual rationality. Okay. Make sense? Okay. So, when I say ex post IR here, it means the same thing. Okay. When I say ex post IR, it means the same thing. If the click probabilities are not known, click probabilities are generated stochastically. Here the only thing is I am still taking the expectation, but not with respect to the valuation of the agents, but with respect to the clicks. Okay. Similarly, ex post incentive compatibility, similar thing. It is incentive compatible irrespective of what the valuation of the other players are. okay, but not with respect to the adversarial clicks, but by taking the expectation of the adversarial by taking the expectation of the clicks. Okay. So, this was the result. Okay. So, this was when the click probabilities are unknown, that means I do not know, I am learning with the mechanism designer. So, basically what we are doing in this particular result, we are basically taking the advantage of unknown thing to the agents, because they do not know, they will behave rationally with respect to the only information that is available to them. Okay. The second thing that we did, sometimes in a practical world, actually this is the two extremes. The click probabilities are actually, it is not right to say that click probabilities are completely unknown. It should be known, sorry. It should be with known click probabilities. Okay. So, it's not the case that it is completely unknown, it is, you learn it over the time, right. But sometimes, for example, from my competition or from my past behavior, I have some estimates on the click probabilities. Okay. In that case, this EPIC is not possible, then what you get is the asymptotically EPIC. Okay. Yeah, please.
How is individual rationality different from normalized mechanism? In both cases, participation is based on whether utility is greater than 0. So both are same.
Yeah, both are same. Yeah. I don't know why, because yeah, it should be same. Because in the other paper, when they talked about the normalized, so when we talk about this result, right, they don't talk about individual rational, but they talk about the normalized mechanism. It should be same. Yes. Yeah. Okay. Any other question? Okay. So, again, the intuition is to basically in research how you get rid of these impossibility results. Okay. That was the intuition. So, what we did is we basically relaxed some assumptions, as you generally do in the game theory. So, now what I am going to do is, we have done multi-arm bandits, okay, we have understood multi-arm bandit mechanisms. What I want to give you is the positioning of the theoretical result, what all things are there and what all things are open in the literature. Okay. So, before that, there are few things which we have not covered, but let me give you some intuitions. So, what we did is, there are two kind of approaches to solve the multi-arm bandits. The first is called the frequentist approach, which we have seen. So, that is what your UCB kind of the approaches. Okay. The second is called the Bayesian approach. We have not done the Bayesian approach, so let us skip it, because it was planned in the first lecture, but because of time. So, I will not focus on the Bayesian approach, let us focus on this approach. Okay. So, now in the multi-arm bandits, what we have seen is a very simple problem. What is the simple problem? At every time t, I need to select one particular arm, okay, so as to maximize some reward. Okay. However, when you go to a more practical setting, even to the setting of the sponsored search auction, okay, you are not selecting one arm, but you are selecting multiple arms. Okay. So, in that case, this goes to what we call as the multiple pull. So, at each time, instead of selecting one arm, you are selecting multiple arms. Okay. So, this is the multiple pull setting. Okay. In the single pull setting, again you have something called the deterministic mechanisms and you have something called the randomized mechanisms. Okay. Now, the good thing about deterministic mechanism, obviously they are deterministic, but what we have observed when we were basically doing our research in multi-arm bandit mechanisms, the randomized mechanisms, right, they are not what do you say, So, randomized mechanisms, when we implemented the randomized mechanisms, what we observed is that in expectation, yes, they were truthful, but the variance was too high, okay, especially if I talk about individual rationality, right. In expectation, they were individual rational, okay. However, with some instances what was happening, it was giving very negative reward to the agent in few instances, because it is randomized, right, with some probability it will give. And when I say variance is huge, that means sometimes it was giving too high highly negative reward, and sometimes it was giving highly positive reward, which is not good in the ideal world. You do not want this much variance. So, therefore, in multi-arm bandit mechanisms, randomization is really not something which is worthwhile, especially when the agents are not risk taking agents, right. When they are not willing to take too much of a risk, then these kind of randomized mechanisms are not the good mechanisms, okay. So, in this we had some work. So, this particular, these are the two papers, the landmark papers from who basically started this MAB mechanism area. So, they basically came up, both the papers simultaneously came up with the impossibility result, saying that exploration separated mechanism, it has to happen, okay. So, what we basically did is we basically but this was only related to the single pull, single pull, and the rewards were linear. What we, I think I can skip a bit because I need to explain too many things. Okay, let me try. So, here what we did is we basically the rewards, right, in this particular reward over a period of time is linear, right. So, it is mu1 t plus x1 t plus x2 t plus so on and so forth. We basically extended to the non-linear time varying reward. In the randomized allocation in EC 2010, this was a paper which basically resulted in a significant variance that I have already told you. So, what we basically did is within this framework only, we defined a mechanism which gave me the low regret and the zero variance. However, this mechanism actually gave the weaker guarantees on the incentive compatibility that we already discussed, right. These problems are still open if somebody wants to pull. Okay. So, multiple pull mein, so when I am pulling the multi, so not much of a literature is available here. So, even if you see a simple multi-arm bandit problem, you will find a lot of research in the single pull domain, but very few in multiple pull. So, what happens in multiple pull is that the ranking matters. Okay. So, proving the regret guarantees is not as straightforward as it was the case in the single pull. Okay. So, there are a lot of things that is possible in the multiple pull domain, which I think you can try. Okay. So, again what happened is these two papers basically proved the similar impossibility result for the multiple pull. Similar impossibility result mean that even when you are doing multiple pull, it has to be exploration separated. Okay. But what we did is we basically used the randomized payment and randomized allocation here, and we proved that in multiple pull again you can design the mechanism which is exposed incentive compatible and still focus on the multiple pull. Okay. These are still open. We will skip this. Okay, questions still here.
Can we convert the multiple pull problem into a single pull problem by taking like subsets, considering subsets and then their individual?
Good question. So, if you see, if you basically consider the subsets, you can, I mean no doubt about it, but then your search space becomes huge. It becomes 2 to the power n, right. Then you might not even have that much time to basically explore all possible subset, and it is a very inefficient way to do this. Make sense?
But still can apply all these things.
So what happens is, so let me give you some ideas about the subset selection. So what happens in subset selection is, now there are two kind of things that are happening, two kinds of setting that you can consider. So one is called the semi-bandit feedback and one is called the bandit feedback. Okay. So what happens in semi-bandit feedback in multiple pull is, let's say you are selecting a subset. In semi-bandit feedback, what happens is, you basically realize the reward of the individual arms that you have selected. Again, you are getting the feedback only for the arms that you have selected, but you get individual feedback of all the arms that you have selected. And then you can assume reward function whatever you want. It could be linear, it could be, you know, some function or something. If you know the function and if you are observing the individual rewards, still the ideas are very similar to what we have discussed. Then it becomes the ranking kind of a problem. Okay, this ranking could be different based on the function. Does it make sense? The more tricky situation is when you have the full bandit feedback. In that, what happens? When you select a subset, you only get to observe how this subset performed. You do not get how the individual people are. So imagine the cricket team selection, and then you selected a team individually. I mean, you get something, but you basically understand how this team overall performed. You do not get the individual feedback. Okay. So that is a bandit feedback. There the problem becomes tricky, and it is a very, very active area of research. What kind of algorithms work there? Okay. So there what people do is the following. Even though you are receiving the bandit feedback, they assume something on the reward structure. So let us assume that even if you are getting the bandit feedback, the reward is still linear. That means each and every arm has some inherent quality, and when you pull this subset, the reward that you get is the sum of these inherent quality. You do not understand what is the actual reward, but it is sum that you know. Okay. Then how can you compute the individual quantity? I can just do it with the marginal contribution. So let us say you want to find my quality, then you pull, you basically select me with the other people, and then you select the other people and take the difference. That is one possibility. Now you might have a constraint that every time you need to select only k people. Okay, then the approach that I told you will not work, because you need to include someone else. Okay. Then also there are methods, but the basic idea is you assume something on the reward. Another reward model that people are using is the submodular reward. If you know it, it's good. If you don't know, it's perfectly fine. Okay. But you, the basic idea is you kind of assume something on the reward model so that you can estimate something, so that your itna bada search space gets shrink. Okay. But I do not know anything yet on the bandit feedback plus mechanism design. Okay. Any other questions? Are we okay? Good. Okay, so now the last thing that I want to do is take a case study. Okay, and this case study is called the demand response, because this problem of multi-arm bandit, as I told you, is a very, very it's a good theoretical problem, but it also has the good number of applications, right. So, one of the application apart from the others which I have worked on is called something called the demand response. So, let me tell you what this practical problem is. Okay. So, in the demand response I have something like this. Okay. So, I have something here is my distributor company, and what happens, so it is an electricity smart grid kind of a situation. So, I have a distributor company which basically distribute the electricity to different type of houses. So, there could be some small houses, there could be some industry, there could be some big houses. So, different types of consumer it basically distributes the electricity to. Okay. Now, in order to meet the demand of this distributed electricity, what happens is distributor company typically learns a demand curve. Okay. We are not focused on how this demand curve is learned, but there is some demand curve. Okay. And but what happens is when the actual time we have to supply this electricity, this demand curve can be very different from the actual demand. We know uncertainties ke karan, right. So, this demand curve is there, and based on this demand curve it basically makes some necessary arrangement, but the problem that we are facing is what happens when the actual demand is significantly different from the demand that you expected, and especially when the actual demand is significantly higher than this demand, then what do you do? Okay. This is the question that we want to ask. Okay. Now, in typically what happens is in such cases distributor company basically buy the extra energy from the shorted whatever shortage it is facing from the market. Now, buying from the market is very costly. So, it incurs a huge cost for buying. Make sense? Okay. The question that we are trying to do here, on the question that we are trying to pose here is that can we somehow, instead of buying the electricity from the market, can we somehow incentivize these customers to basically reduce their peak load, reduce their load. Is the question clear? So, instead of buying from here, you are basically incentivizing these customers to reduce their load. I do not know whether they will be able to reduce or not. Okay. And this is something which I am learning over a period of time, how much uncertainty is associated with each and every customers.
The customer, whatever it is paying to the distributor company, that is always more than the purchased electricity from market, right? Or it's less sometimes.
So, typically what happens, not in India, at least outside, the price that each and every person is paying depends on the peak usage, right. So, if the peak is higher, then they end up in paying much higher amount per unit of consumption as compared to in the low peak, right. So, like in the afternoon the charges would be lower as compared to the mornings or evenings. So, this is what generally happens. When we discussed this problem of giving the incentives, what we mean is that there is some prices that each and everybody is giving, which could be varying with respect to the peak things, but what you do is you basically give them some offers, right. So, let us say this person is paying x rupees per unit, then you say that instead of x, if you reduce let us say by 1 unit, then instead of x you pay x minus epsilon, you give some offers. Okay. And the question is what kind of offers should you give? You do not want to give too high offers, because otherwise you will incur a loss. Okay. You do not want to give too less offers, because what will happen, otherwise they will not end up in reducing the consumption. Is the problem clear? Okay. Okay. So, again we basically formulated this problem via multi-arm bandit approach. We basically wanted to see this. Okay. So, what we did is this is the very simplest setting. Okay. This is the first work that we did sometime in 2016, I guess. So, the idea is to basically learn the behavior of the consumers via multi-arm bandits. Okay. And what you want is you want to design the intelligent pricing schemes via some game theoretic solution, and you also want everything to be profitable. Okay. So, what is the utility model that we had? So, again consider a very simple setting. I have a certain type of consumer. Each consumer basically is associated with some PI, which basically denote if I give some offer to this consumer, with this probability it will reduce its demand by 1 unit. This is PI, similar to your click model. Okay. The thing that we assumed, and we will relax it in some other in future, is that we assumed that whatever you are basically okay. So, whatever offer you are giving, each consumer basically has some valuation for that electricity. That means, C1 denote that this consumer will not reduce its electricity until and unless it gets the money C1. So, C1 represent its valuation per unit of electricity. Okay. So, now the idea is you want to elicit this C1 truthfully while learning these PIs. The simple assumption that we made in this work is that PI and CI are completely unrelated. Okay. So, you assume that PI kind of represent the uncertainty. So, suppose in a house the distributor company gives an offer, and then you say that this house ideally will reduce the electricity, but with certain probability it might get some visitors. Okay. In that case it will not be able to reduce the electricity. So, what is the frequency that the visitors will be coming to the house? So, it captures some kind of uncertainty. Make sense?
How will the offer look like? Like what kind of an offer will the
So, currently I am just looking at a very simple offer. I will just pay them C1 amount. Okay.
at time t or like this?
It's because C1, CI and PI are independent of time. So, whatever time I choose the customer, I will simply decide based on CIs and PIs.
And in return, what should the consumer do?
It will reduce the electricity by 1 unit. Does it make sense? Okay. So, you do this, you find, so what you want to do, now it is a multiple pull problem. So, what you want to do, you want to choose the optimal subset of consumers. Okay, which consumers you should offer the electricity price to reduce to, so that to minimize the loss to the utility company. Okay. Now, the problem here was as follows. So, when I talk about the loss to the utility company, the loss is not simply linear in terms of the shortage. Okay, because it is coming from the electricity, it is generally quadratic. So, if I face D amount of shortage, then the cost that I need to pay is some fraction of D square. It is a squared loss. Okay. So, now it is no longer linear, it is a squared loss. Okay. So, I do something, okay, but the main thing that I wanted to tell is, okay, with PI probability it will reduce the consumption and I will end up in giving CI truth. Okay. So, summation CI is the expected loss. Okay. I will come to the second term later. This term is basically this is the expected reduction that I will get. Summation Pi is the expected reduction that I will get, and dt is the shortage that I am getting. So this basically represent, the square basically represent how far I am from the shortage. Okay, this is this function. The second term represents some kind of variance. Okay, so I want to minimize the variance in terms of this reduction. Okay, I don't want too much uncertainty when I'm giving the offers. So first term is the loss, third term is the expected cost the distributor company is paying, and the second term is the variance. Okay, I want to minimize this function. Makes sense? Okay. Now, this function is, first of all, this function is supermodular function and non-monotone. How many of you know these terms? Submodular, supermodular. No. Okay, so let's skip it. Okay, in the interest of time. It's perfectly fine. But the main thing that I want to talk is, this is non-monotone supermodular. It's not easy to come up with an algorithm which basically selects the optimal subset. Matlab, until and unless you basically see all the possible combination, root force approach, the really kind of the algorithm doesn't work here. Okay? So what we did is basically, again, focus on the intuition. I'll tell you the intuitions about the proof, but just understand that how we reach to the solution. Okay? So we know that it is not difficult. So we wanted to learn this PI, right? And we wanted to elicit this CI. But before that, in a typical multi-arm bandit problem that we discussed, the comparison is always with the optimal offline algorithm. So whenever you are trying to come up with a multi-arm bandit-based algorithm, if your algorithm is not with linear reward or with something, you will have to first define the optimal. Does it make sense? We were comparing with mu star. We knew what is optimal. Okay, here we don't even know what is optimal. Okay, so the first thing that you need to do is you need to define the optimal thing. What is optimal? In this case, my optimal set will be the set which will minimize this. Okay, and the optimal reward will be something which the value of it. Does it make sense? So in order to come up with a multi-arm bandit based algorithm, we need to understand how the optimal algorithm will look like. Even if the algorithm knew everything, even if the algorithm knew PI, even if the algorithm knew CI, then also how will it select? Okay, and it's not an easy problem because the rewards are not linear for the multiple good setting. Does it make sense? Okay. So then what we did is the following. We basically tried to find out how the optimal solution will look like. Just we were trying how to find, and then we thought, okay, let's say you have some S star, okay, which gives the best. So here I have SD star because my demand is dependent on the T. How will it look like? Okay. We have this now. So we said that in any ST star, which basically minimize this loss function, if at all I am selecting the GF agent, then its cost could not be too much. Okay, don't focus on the expression that I am giving. This particular thing, how we did is simple. Suppose ST star is optimal. Okay, and you choose a particular agent J which does not belong to ST star. Okay, so then the loss with respect to ST star, okay, minus the loss with respect to ST star union J, this should be less than 0. Does it make sense? So what I'm saying is the following. So suppose I have J which does not belong to ST. Okay, then what this is saying is the loss with respect of the set ST star minus loss with respect to ST star union J. Because this is optimal, this loss should be less than this. Okay, this should be less than 0. Okay, now if you substitute the loss expression from the previous slide to here, you will get a condition on Cj. Is it okay? You will get the condition on Cj. Similarly, if J belongs to ST star, then also you do the similar thing. You basically compute L of ST star minus L of ST star minus J. What happens if J does not belong? Then this also should be this loss will be bigger than this loss. It will be negative. ठीक तो है? It's okay, right? Okay. If you simply substitute these things in the previous thing, you will get such kind of lemma. Okay. And based on this, you will get this corollary. I will skip this. Okay, then what do you have this session? Was any? How?
I think we can already. But the settings around 30 to 12.
11:30 to 12:45. Oh. Here. I guess we started slightly late, so it's okay. I'll just take 10. 5 or 10. Here. Is this okay? Good. Okay. So once we got this characteristic, now we don't know this is, so some local optimal solution should satisfy this characteristic. Then we came up with this algorithm somehow. What we did is, this is some kind of a greedy algorithm, which basically said that you arrange the agents in this order, C, Pi minus Ci by K. Okay, and then if any agent I which you want to select in this order, if it satisfies this condition, then you add I, otherwise you don't. And based on that, you start filling your set. Okay, and then we prove that this particular set is what is called the local optima. Okay, I will skip this, but the idea of proving the local optima, again, focus on the intuitions. The idea was basically saying that if suppose I had added this agent, okay, then after I add another agent, this agent will not move out of the loop. This agent will still satisfy these two characteristics. So every time I am adding the agent, there are two things that will happen. That my already added agent will still satisfy these characteristics, and my already rejected people will also satisfy the characteristics. These were the results. Okay, but more importantly, what I want to finish with is, how do you convert this nice, we showed that this nice 3D algorithm works if you know PIs and CX. Okay, but you don't know PIs. How do you extend to the multi-arm matrix? Okay, the similar concept, what you do is, you basically, you don't know PIs, and you know that higher is the PI, higher is the probability of selecting this particular person. Okay, so then what you do, you basically make an optimistic estimate about the agent I. Okay, so that it becomes better in ranking. Okay, so here you make optimistic estimate on PIs. That idea same hai. It's the same idea that we have been discussing. So you make optimistic estimates on PI. Okay, and then when you are deciding whether to consider this person or not, the problem is these PJs also you don't know. Now, if you are considering the optimistic PJ, then the probability that you end up in selecting the ith agent will reduce. Because if PJ will increase, this term will increase, then CI by 2 will be less than, may not happen. Okay? Because you want to give enough chance to ith agent, here instead of taking the upper confidence bounds of PJ, you take the lower confidence bound of PJ. So that you are giving the optimistically chance of to agent I. Okay? Does it make sense? So the algorithm then is pretty simple. In here, you give the upper confidence bound. So PI hat positive implies the upper confidence bound. Whereas in here, you consider the lower confidence bound. Because you want to basically give the chance to the ith person as better as optimistically choose this. Okay? Intuition wise, it was good. The hardest part was proving the regret. Okay? But again, the ideas were similar, although it required a little bit more intrication. But the ideas were similar. Okay? So that it did the regret part. Okay? The second thing that you had to do, PIs. Okay, good thing. So we now understood how to learn PIs. We just applied multi-arm bandit, simplest tool, optimism in the face of uncertainty. We just gave the optimistic speech. We just consider the optimistic. Okay? The second hurdle is CIs are not known. Okay? But yeah, we didn't bother about it. What we did is we basically took this randomized allocation and randomized payment rule from the Babai of the EC 2010 paper, and which basically told us that if you have some kind of monotonicity allocation rules, then that particular randomized will give me some payment. Okay? Now, again, the question on the option heavy. Do you know about monotonicity in allocation rule, which is a necessary condition for the truthfulness? You know, right? What is monotonicity condition?
Increasing the value should not decrease the...
Exactly. So, if my allocation rule satisfies the monotonicity property, which is the necessary I require, right? Then I can simply use my randomized paper there and use their mechanism. Okay? So, the only thing that I need from my algorithm was that it satisfies the monotonicity property. Which it does, because this is, not hard to prove. If my CI is higher, then I get lesser probability of getting selected. So because it's a cost setting, you want it reverse. So lower the cost, higher should be my probability of getting accepted. That's what monotonicity is in this case, because it's a cost model. So whatever monotonicity you set, higher the valuation, your chances should improve. Here it's reverse. The lower the cost, your chances should improve, which happens naturally in this kind of a set. Okay? Good? That's all. So now there are multiple ways we have been working. So this, I started this work in 2011, then we did something in 2016. Recently we did something in So then we kind of
extended it with some change of definition. This happened in 2021, and recently 23 what we did is another interesting thing. Okay, so the interesting thing that we get is the earlier model. What we assume is that the cost, okay, does not depend on the PI, the probability of reducing the consumption, does not depend on the cost. How much offer you are paying, it does not depend, right? However, that's not the case in general, right? If I get more offer, my chances of reducing the electricity becomes better and better. Okay, so in this work, we kind of assume there is a function, and instead of learning that, we kind of learned the rate of this function. So that was the reason. And that's all. And the takeaways is it's an interesting area. Multi-arm bandits and mechanism design happens in many, many, many applications. So you might look into it. And these are some of the references. Thank you.